Hey there. Okay, we got another quiz video. In this case, we have a moon that's going to be wrapped in metal. So it's a metal sphere, essentially. And you're going to need a little bit of more information. You can get it from your book. Pretty straightforward. You have to determine the capacitance of the moon. So we're going to go ahead and get started. And if you go to the end of the video and you don't have the same answer, then come back to this point. Okay, so we need to be looking at this in terms of, the capacitance of a sphere, which might sound weird, but before, when we looked at the capacitance of a parallel plate, we have to remember that that's only one type of capacitor, right? Really, when it comes to capacitance, the whole idea is what voltage does it take to store charge on an item, right? So it doesn't have to be that you move charge from one plate to another plate. It could be that you just took charge from elsewhere and just sort of stacked it. So that's what we're doing here. We have one sphere, not two. We just have one sphere, and we're asking if we bring in charge from very, very, very far away and stack it on the moon, then what voltage would you get for every bit of charge, essentially, is the way that that works out. That it defines what the capacitance of the moon is. Now, we've been through this already, and the hint here that you have is actually helping do what we already did in our derivation of the capacitance of a sphere. And it doesn't hurt to kind of go back through that again. The definition of capacitance, remember, is the charge over the voltage, so the amount of charge per unit voltage that something has. And if we have a sphere, then essentially what we're doing is, like I've mentioned before, that if we have a radius of the sphere r, then the voltage on that sphere given a certain charge is going to be when I put the delta here, I'm essentially saying the difference in voltage between this point that of interest and some very infinitely far distance away. So that is given by kq over whatever the radius happens to be, which works again for anywhere outside the sphere, including the surface, right? So we'll use the actual radius of the sphere for our voltage. And so what that means is that we're going to take C and we're going to replace, we have Q upstairs here, and voltage downstairs, which means 1 over V is going to be the reciprocal of this. So we'll have K and Q downstairs and R goes upstairs. So, okay. That means the charge is going to cancel, and essentially the capacitance here is the radius of our sphere, which in this case is the moon, over our Coulomb constant. So we need to look up information on our moon. It helps to look up when you're in this course. If you're not looking it up in the book, I'm just kind of Googling it. It helps to use the SI unit, because otherwise they have a tendency to try to hand it to us in miles, which isn't really that useful for what we're doing. So we have 1.74 times 10 to the 6 meters. Okay, let's go back to our problem and plug that in. 1.74 times 10 to the 6 meters. And our Coulomb constant, of course, is just 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. 194 microfarad, which is, I'll try to bring up a little capacitor into class so that you can kind of see the kinds of capacitors we use on electronics we regularly use up to 3,000 microfarad capacitors in electronics. So obviously, spheres are not a very good way of holding charge, right? Because it takes one the size of the moon in order to hold, a charge that is reflective of about a 200 microfarad capacitor. That's not a very good device. Okay, I'm gonna wrap this up. Okay, if this is not the answer you got, then go back to the beginning, compare notes, and let me know if you got something else.